Welcome to our presentation. The topic of our paper is efficient forgetting what you have learned in graph representation learning while projection. As privacy protection received much attention, learning the effect of a specific node from a pre-trained graph neural network model has become equally important. However, due to the new dependency in graph structure data, representation learning in graph neural network is challenging and is less well explored. To see why no dependency could cause graph learning challenging, let us refer to the figure below for an illustration. This figure shows that how the node representation of a two-layer graph neural network with mean average aggregation are affected after deleting node 4 from the graph. We can see that the node representation of node V2 and V3 are also affected since those nodes require node 4 to compute their representation. Such dependency grows exponentially with respect to the number of GNN layers. Motivated by the importance of learning in graph structure data, we aim at answering the following questions in the context of GNNs. Can existing machine learning method be utilized to solve the graph learning problem? The answer is no. This is because most of the existing machine learning methods are designed for settings where loss functions can be decomposed over individual training samples. And the node dependency in graph structure data render these methods inapplicable to GNNs and make them suboptimal. Then, our next question is, can we efficiently learn representations in GNNs in a computational efficient manner? The answer is yes. We propose a projection-based learning approach for linear GNN that not only bypasses the node dependency issue, but also enjoys the perfect data removal guarantee. More specifically, we propose to unlearn node features by orthogonal projecting the linear GNNs with parameters onto a subspace that is irrelevant to the unlearned node features. The projection step guarantees our weight parameters do not carry any information about the deleted node features. Our method can bypass the node dependency issue because the graph convolution in linear GNN can be reformulated as a linear combination of the input node features, and the projection step is directly applied to the node features. Notice that this is different from most of the approximate learning approaches, because their gradient and Hessian are computed on the output of the GNN model. Thereby, they are affected by the node dependency issue. Then, our third question is how to assess the effectiveness of learning in GNN. In this paper, we consider two criteria to evaluate the effectiveness of learning. Our first criteria is to measure the distance between the unlearned weight parameters to the exactly retrained weight parameters. We evaluate this criteria by selecting upper bound the distance of two models. We show that our method enjoys a tighter upper bound than the approximate learning method in Theorem 1 and Proposition 2. Although these criterions has become the de facto way to measure the success of learning for approximate learning method, we theoretically show that we cannot infer whether the data has been deleted solely from it, as in Theorem 2. Therefore, we introduce our second criterion by checking whether unlearned weight parameters contain the deleted node features. To achieve this, we introduce feature injection test in the experiment section to rigorously verify this criterion. In the experiment, we compare the closeness of the unlearning solution WP to the retrained model WU to verify our conclusion in Theorem 1 and Proposition 2. Ideally, a powerful learning algorithm is expected to generate similar weight parameters and activations to the retrained model, as shown in the figure 3. Both the final activations and output parameters of our method projector is closer to the weight obtained by retraining from scratch, comparing to the baseline method, which could reflect our result in Proposition 2. Besides, we can observe that lower learning percentage will lead to a smaller difference on the output weight parameters of our method projector, which could reflect by our theoretical result in Theorem 1. To verify whether a learning weight contains the deleted node features, we conduct feature injection test. This feature injection test is designed to verify whether the projector and baseline could perfectly unlearn the trace of deleted node features from the weight parameters. To achieve this goal, we append an extra binary features to all nodes and set the extra binary feature as 1 for the deleted node features and 0 for other nodes. To make sure this extra binary feature is heavily used during training, we add an extra category and change all the deleted nodes to this extra category. Then we pre-train on the modified dataset. We measure the effectiveness of unlearning by checking whether a learning method can fully unlearn by comparing the weight parameters of the injective channel before and after unlearning. We also check whether a learning method hurts the model performance by comparing the accuracy before and after unlearning. Moreover, we compare the computation cost by comparing the time required for unlearning. The results are summarized in the table. By comparing the weight norm of the injective channel, we observe that GraphEraser and our method projector can perfectly unlearn the deletion node and setting the extra feature channel at 0. However, baseline method influence and feature cannot fully unlearn the correlation because they approximate unlearning method. By comparing the work clock time, we note that our method projector requires less time to unlearn compared to the baseline. When comparing with retraining from scratch, our method is slightly better than retraining because our method projector could be thought of as an reweighting on the remaining nodes, which allows our method to behave similar to the model before unlearning, but without carrying any information about deleted nodes. Interesting future directions in graph unlearning including designing exact unlearning method for nonlinear neural network with theoretical guarantee. Also, we could design some unlearning method that is not based on the differential privacy.